How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at the wave behavior of matter and the uncertainty principle. So our objectives will be to describe the wave nature of all matter, calculate the Bruy wavelength for various things, and describe the significance of the uncertainty principle. So let's start with this guy, Louis de Bruy. What's he all about? Well, he's a scientist, and he's like, hey, it's weird how light can behave like a particle. I have a crazy idea. If light can behave like particles, maybe particles can behave like light. I'm going to test it. So he does, and he proves that matter, in fact, behaves like a wave, and gets a Nobel Prize in 1929. So he's a super cool guy. But let's jump into it a little bit more. So he found that the wavelength of all matter is equal to that Planck's constant divided by the momentum, right? M times V, mass times velocity, is our momentum. The lambda is our wavelength, and as the mass approaches ordinary objects, like a marble, something that has, mass, a significant amount of mass to it, the wavelength gets so small that it isn't observable, meaning that the wavelength's like less than the wavelength of light, so you're not even going to be able to tell that it's behaving like a wave. But for tiny masses, like an electron, the wavelength is large enough to be observed. So I'm trying to demonstrate this so you can see the very large object is like kind of moving. It's hard to see the wave function of it, but an electron, since it's got less mass, is going to behave a lot more like a wave than something with more mass. So what? Well, let's practice doing a little math, right? So what is the wavelength of a baseball with a mass of 145 grams traveling at 40 meters per second, which is about roughly the speed of an average fastball? All right, so first I need kilograms because that's my SI unit for mass. And I have this formula, so I'm just going to plug some stuff in. I get H is 6.63 times 10 to the negative 34 joules seconds divided by 0.145 kilograms times 40 meters per second. And I end up with a wavelength that is super tiny. To give you an idea, an average atom is like, you could say roughly 5 times 10 to the minus 10 meters wide. And the wavelength that we just got for this baseball is way smaller than that. So when we are describing the location of a baseball, we can be pretty certain because its wave part of it is really, really tiny. So it's insignificant. But what about for an electron? Let's say an electron has a velocity of 5.97 times 10 to the 6 meters per second and a mass of this, 9.11 times 10 to the negative 31 kilograms. What's going to happen to the wave function there? Well, same formula, same plug-in and chug-in, except we got to use the numbers for the electron. And we end up with a wavelength of 1.22 times 10 to the minus 10 meters. And then, once you know it, that's about the same wavelength as an X-ray. So based on what we know about an electron, they should have a wave function that's similar to that of an X-ray. Should behave similar to an X-ray. That's something we could test. So let's test it. We know that when light is passed through a crystal, it interferes with itself, and we get some interference patterns. We know that electrons do this, right? So if we shoot a beam, X-rays do this. So if we shoot a beam of electrons at the crystal the same way we would do X-rays, we should see similar things. Right, so if this is what an X-ray is doing, let's do it with an electron, see if it does the same thing. And it does. We see that. It does the same thing. It's nuts. Right? So further proven, this Louis de Bruy guy and his idea. This is actually how we use electrons to take images, right? The electron microscope. So how defined our images are is based on the wavelengths that we're using. So wavelengths of visible light can only see so finely, but electrons with a much smaller wavelength, we're able to see in greater detail because of the smaller wavelengths. All right, so now that's the first part. That's good. So we know now that electrons behave like waves significantly. Well, all right, what does that mean? Well, we know with classical physics, we can describe where a ball is rolling down a hill pretty accurately. We can tell you where it is at any point in time. We can tell you how fast it's moving. We can tell you all that. It doesn't have much of a wave property, right? We did it for a baseball, and we saw that it's like significantly smaller than any kind of atom or anything like that. So classical physics works for that. But can we do the same thing for matter that has a significant wave property like an electron? Can we still do that for electrons? Well, this is where Heisenberg's uncertainty principle comes into play. It's inherently impossible for us to know both the exact momentum and location of a subatomic particle in space. So we know subatomic particles have significantly larger wave properties because their masses are a lot smaller than what we encounter every day. So what does this mean for our understanding of the atom? Right? So if I have an electron, it's moving all over the place. It's got a significant wave function to it. How am I going to describe where that electron is? What is the atom going to look like if that's what electrons are doing? So here's the formula. This is the mathematics for Heisenberg's uncertainty principle. We have this kind of delta x, which is our uncertainty in position. We have this delta mv, which is our uncertainty in momentum. And it's got to be greater than or equal to Planck's constant divided by 4 pi. So as we know more about one thing, the position or the momentum, we must know less about the other. If we know with great certainty where something is, we can't know with great certainty its momentum, or vice versa. So the analogy that I go to is, like, say you're a photographer, you have a camera, you can control the shutter speed and all that stuff, and a car is driving by at a certain speed. You can take a picture with a slow shutter speed and you end up with a blurred photo, right? So that's the picture you took because the car was moving. In that picture, you know more about the momentum because it's blurred. You can kind of tell where the object is moving, but you know less about where it is at that given moment, right? And the opposite could be done. You can take the photo with a quick shutter speed and the car's going to look motionless. So now I know more about where the car is, but I know less about its momentum. And that's kind of what the uncertainty principle is saying, right? So here's another, going back to the baseball example. What is the uncertainty in location for a baseball, 145 grams, traveling at 40 meters per second? And let's say we have a 1% uncertainty in our speed. We measured it to be 40 meters per second within 1%. Well, our uncertainty in position's going to be equal to this. It's got to be greater than or equal to that. So let me just plug in those numbers, and let's see what I end up getting. I get 9.09 times 10 to the negative 34 meters. I forgot my units. And that's significantly smaller than even X-rays. So the uncertainty in position is like virtually nothing. So we know exactly where that fastball is. But what about for that electron? You know, is it still going to be as simple as those planets orbiting the sun? Is it going to look like that? Well, let me plug in some information. All right, I know the mass of an electron is at 9.11 times 10 to the negative 31 kilograms. I know its average speed, and let's say my uncertainty is 1% of that. So now I can plug and chug, and I get the uncertainty in position to be 1 times 10 to the minus 9 meters. Well, what does that even mean? How big is an atom? The diameter of an atom is even smaller than that. It's 2 times 10 to the minus 10. So the uncertainty of where an electron is actually a lot bigger than the actual size of an atom. So we don't actually know the specific location of an electron. We can't describe, oh, there it is. That ain't going to happen. You know, being like, oh, hey, I found it. You know, like, where's Waldo? I found it. It's right there. No, this electron is all over the place. And we can't actually know with any real certainty where it is. But we can describe where it probably is, like an area where you would find it. And that's where the quantum model comes into play, or the electron cloud model. So you can see in the center there's the nucleus, right? So when we're trying to describe what it looks like, well, the electrons aren't orbiting like planets anymore. They're kind of this cloud of uncertainty. So we can color it in and go, all right, where it's more colored, that's where you're more likely to find an electron, but you're not going to be able to pin it down and go, there it is. All right, so summarize. Can you describe the wave nature of all matter? Can you calculate the Bruy wavelength for various things? And can you describe the significance of the uncertainty principle? I hope so. Okay, bye.